Alright students, so I'm going to now look at this idea of apparent brightness and then hopefully get into Stefan-Boltzmann's law, where we compare the luminosities from different stars, and we're going to also try and see if we can get through to Wien's displacement law, but maybe we won't get quite there. So to help us with this, I'm going to go here. I've got a sort of a small diagram here, and this is the idea. This is the sun over here. There's the sun, and this is the earth, and we can imagine the sun is radiating in all different directions energy. It's coming off, and on the earth here it will be getting only a small fraction of that energy. So the luminosity, which is, as we saw before, is the total power, is being spread out in like a giant football, a giant sphere. And here on the earth we will just get a small fraction of the total power. Now we define something called the apparent brightness. The apparent brightness by this. It's the energy that is received. Basically the power per unit square meter, per square meter that is received. So it's the power per square meter, and we denote it by a b, a small b. Now if you think of this, if this was a giant sphere, the total surface area of this whole sphere here in 3 dimensions, that surface area is actually given by 4 pi, and I'm going to use d squared, where d is the radius from the inside there to there. That would be the surface area. So from this, the power per square meter, the sun gives out a certain amount of power. It's giving out is the luminosity, the L. So the B is actually given by this formula. The B is equal to the luminosity divided by 4 pi d squared, where d is the distance that we are away from the sun, or away from the star, whatever it may be. Now this b is measured in different ways. On the earth, from the sun, you can measure it by different ways. You can measure it through a telescope. In the textbook it talks about putting a bolometer, something like this, B-O-L-O-M-E-T-E-R, to a star, onto a telescope, and that can measure the apparent brightness from a star. You can have other different means which you should look up. So that is our apparent brightness. It is the power per square meter that is received at a certain point. Power per unit area that is being received. I think I'm going to go on to just one further thing here, and I'm going to look at Stefan-Boltzmann's law. So we will have a look at that. Now, Stefan-Boltzmann's law relates to something called a black body. Now, a black body is a perfect emitter. Now, the sun we would classify as a black body, and basically what the reason for this is because it releases all its energy. It doesn't store any. I mean, it takes quite a while for it all to come out, but in the end result, it gives out all its energy. So it's a perfect emitter. This is the idea of a black body. Now we get other black body sources such as a light bulb that could be studied in the laboratory. And in studying in the laboratory, they found that there was this relationship between the luminosity of a black body is given by this formula. We have sigma, which is Stefan-Boltzmann's constant, times the area times T to the 4. So basically the luminosity is proportional to T to the 4. It's also proportional to the surface area. Now this surface area, usually we're dealing with a sphere. This area is again given by 4 pi r squared. So we can put that into that formula. So this is Stefan-Boltzmann's law. It's extremely useful. It's extremely useful in dealing with stars and so forth, because stars are black bodies. So we can apply this law. If we know the luminosity and we know the temperature from that, we can estimate the surface area, and from the surface area we can have idea of the radius. So this is Stefan-Boltzmann's law. I think I'm going to leave it there, and in the next one I'll talk about Wien's law. Thank you.